Hello, I'm Dan Cook with BoneZone, and welcome to our webinar about BioDur 108, Carpenter Technology's latest innovation in cobalt and nickel-free stainless steel for articulating orthopedic implants. Today's webinar is sponsored by Carpenter Technology, which specializes in a versatile alloy portfolio featuring titanium, cobalt, nickel-based, and iron-based materials. The company provides top-quality materials for medical devices that contribute to improved patient outcomes. Joining me today is Ray Dufresne, Manager of Regional Metallurgy at Carpenter. Ray has a passion for developing innovative solutions and specializes in titanium, iron, cobalt, and nickel-based products. Today, Ray will explore BioDur 108's chemistry, mechanical properties, and wear resistance, highlighting its suitability for load-bearing applications such as hip and knee replacements. With that, I'll throw it over to Ray.
Thank you so much, Dan. Good morning, good afternoon, good evening to those joining us from abroad. I just wanted to welcome everyone to our webinar. Thank you so much for joining. Again, my name is Ray Dufresne, and I am the Global Manager of Regional Metallurgy and also the Medical Subject Matter Expert at Carpenter Technology. Today, we're going to talk a bit about a new breakthrough in nickel-free, cobalt-free materials for next-generation implants. And we're going to spend a good portion of time going through some new information about BioDur 108. This session is designed specifically for medical OEMs and contract manufacturers, and my goal is to share not only technical details, but also open the door for opportunities on further collaboration. By the end of this presentation, I hope that you'll see how Carpenter Technology can help you innovate in meeting the evolving regulatory and performance demands in the ever-changing medical community. So first, I'm going to quickly start with just an overview of Carpenter and also the role Carpenter plays in the medical industry. So Carpenter Technology is a global leader in specialty materials. We produce titanium, cobalt-based, nickel-based, and iron-based alloys. We also produce powdered metal alongside of our wrought alloy expertise. And our mission is simple. We want to deliver materials that improve better patient outcomes and also enable next-generation medical devices. So you may have heard me say this before, but we're not just a supplier. We really strive to be a technical partner, and that's a major reason for why we have a webinar here today. So Carpenter serves multiple strategic markets. We support aerospace, automotive, energy, defense, consumer, and medical. And we have over 500 high-performance alloys with numerous custom combinations and compositions beyond that number. And if you've worked with us before, you know that we hold ourselves to a very high standard to maintain the quality reputation that we've built over many years. But what truly sets us apart is our vision to be the preferred solutions provider in the specialty materials. So how we do that is we target being an irreplaceable partner in accordance with our core values. Some of you may have seen this slide before, but I just wanted to add this to the presentation because I think it's so important to reiterate Carpenter's core values. And our core values really guide everything we do, with safety being first. Carpenter works to be a transparent partner, but we hold ourselves accountable to the commitments that we make. We drive ourselves to deliver results. We do that through collaboration, integrity, and respect, both internally and externally. And I know it's easy in a presentation like this to gloss over the core values, but I think it's important to communicate to teams like this and throughout the medical industry that Carpenter is not only rooted in technology and rooted in innovation, but rooted in our core values. And they don't just stop at the company door, right? They go beyond that, and it shapes how we engage with our customers, with folks like yourself. So now we're going to talk a little bit about where we operate. So Carpenter is a US-based company with manufacturing locations throughout the United States. We do have one atomization unit in Sweden with a team there to support. But here in the United States, we break ourselves into centers of excellence with manufacturing processes in Reading, Pennsylvania, Latrobe, Pennsylvania, Athens, Alabama, Huntsville, South Carolina, and our two titanium divisions in Clearwater, Florida, and Washington, Pennsylvania. So in addition to that, from a production standpoint, we do have global distribution locations, and this global footprint really allows us to support needs wherever you are. And with that level of communication and collaboration I talked about, have an ability to have material locally and ready for your support. We'll talk a little bit more about processing and manufacturing innovation before we get into the meat of the technical presentation. So Carpenter, again, I mentioned before that we support collaboration and development. We're also a leader in alloy development and materials process innovation. So yes, we drive innovation in alloy design and development, and ultimately the implementation of new materials like we will talk about today. But it doesn't simply stop at materials. We also have teams working on process development for things like continuous improvement, but also to provide products that boost manufacturability, for example, at your location. So these innovations really combine the know-how internally at Carpenter of our research, our production, our metallurgical, and our quality teams, but most importantly, it requires input from our customers, from our contract manufacturers, from the design engineers. So, as I go through this presentation, especially when I get to the technical part, please think of some questions for our Q&A session, because I think it's important for us to collaborate. So Carpenter's production processes start at the selection of raw materials, and that's prior to any of our melt processes. And depending on the material and its application, we may deploy advanced melt capabilities, such as a vacuum induction melt, or we may need to employ advanced remelt processes, such as a vacuum arc remelt or electroslag remelt, to drive some of the quality standards that we hold ourselves to, and for the component performance that our customers expect. From there, after melting or remelting, our production follows what you see on the left-hand side: hot working operations, thermoconditioning, finishing operations, testing, and finally certification and shipment. So in other words, Carpenter and our mill, we take raw material from bags of elements and turn that into your feedstock product. And while doing that, drive the consistency and quality through our melting process where it is born, through our processing, through our testing, and finally our shipment, while we maintain traceability in our production to drive confidence in the products that we provide to our customers. From a material testing standpoint, and I know I talk with many folks throughout the industry about material testing, qualifications, differences on one lab versus the other, capabilities, but on site, Carpenter has an accredited lab for chemistry, mechanical testing, metallographic testing, corrosion testing. And what that means is that every batch we produce at Carpenter, we're targeting the highest standards of performance and reliability, and we have the capability to offer testing beyond the standard. Whether that's a standard ISO test, standard ASTM test, an AMS test, we have opportunity to drive more data for our customers with their expectations beyond the specifications. So although many of the tests or accreditations you may see on the screen may not be applicable to you today for your device or design, these are things that are available as designs, expectations, specifications evolve. So I would challenge you to consider in your performance and your critical performance variables, what is a driving factor and how can Carpenter support you from additional testing? As I mentioned before, continuous improvement is part of our innovation, and it's certainly part of our DNA. So let's talk about two quick investments and just highlight some changes from a capability standpoint where Carpenter is supporting continuous improvement. In 2018, we did unveil a new hot strip mill in Reading, Pennsylvania, commissioned again in 2018, and that's driving towards reduced lead times and improving precision strip capability. So this supports markets like aerospace, consumer, magnetic applications, and certainly medical applications. And ultimately, by providing a better control on our input master coils, we're really able to ensure a higher quality input product, both from our melt, both from the master coil, and then ultimately a feedstock to our own process to improve the finishing operations. And I mentioned two capacity and continuous improvement items. The second, a $400 million commitment to expand premium melt capacity. So understanding that robust applications require robust materials and processes, Carpenter has really committed to that expansion by driving a new melt facility in our Athens, Alabama plant. This expands our high purity melt capacity and supports continued need of vacuum melted products for mission critical or life-saving, never fail components. So what this does is it really positions Carpenter to support future needs, whether that's scaling production or developing new alloys or communicating to the teams like this that we're going to have material and we're going to have material in the future as demands and designs changes. So now we're going to talk a little bit about the medical market and how Carpenter plays today and how we've helped instrumentally change some of the design expectations within the market. So this slide is really a snapshot of where Carpenter's alloys are used today. This is specific to orthopedic implants, but also goes beyond simple ortho. So we see in this image, we have hips and knees. We see spinal fixation systems. We see surgical instrumentations to vascular stents. Really, our materials are everywhere when it comes to supporting patient outcomes. Our materials are trusted in the operation, in the OR, and in the implant of the individual, really where failure is not an option. So now that you've seen a few of the applications, let's talk a little bit about the challenges in the medical alloy landscape. So historically, the medical industry relied on general stainless steels for implants and instruments. These materials served us well, right? But they came with limitations in corrosion resistance, in strength, in performance. And as you get more and more familiar with materials, the metallurgical challenges of materials, there's almost always a trade-off. And in some cases, improvements were needed. As further biocompatibility needs were needed, materials such as the cobalt-chrome system and titanium products were identified, oftentimes leveraged, honestly, from aerospace applications. So these further needs for improved performance, whether it's for patient safety, for advanced designs, they've exposed gaps on material capability, in strength, in corrosion resistance. And again, I'm just showing this as an example, kind of relative comparison of materials, but it shows and helps identify some of the challenges that have existed within the alloy landscape. So Carpenter has worked with many of the medical OEMs, the design engineers, and the industry at large for decades. We've worked to help identify and respond with innovative solutions, such as the Custom 465, the nitrogen strengthened implantable materials. and most recently, A421. We're not going to talk about that alloy here, but it's another really neat innovation that is frankly very exciting. And if you haven't heard of it, you should check it out. Anyway, Carpenter doesn't just supply materials, right? We innovate alongside folks like yourself and designers and contract manufacturers to solve design challenges and ultimately improve patient outcomes. So certainly we're going to speak quite a bit about BioDur 108. You may have seen it flash here on the screen a moment ago. So please take notice really where this sits in comparison to many of the other alloy systems out there. And if you didn't catch it in the title, it's a nickel-free, cobalt-free material, and it's designed for high strength, corrosion resistance, and biocompatibility. It's positioned as a next generation solution for implants, and it really offers a high level of performance when it comes to strength, fatigue, corrosion resistance, and biocompatibility, much better than some of the legacy alloys. Before we jump into BioDur 108, though, I just want to take a moment and talk about some of the most recent challenges in medical device development, the regulatory changes associated with the EU MDR. So I'm sure most everyone on this call is familiar with EU MDR. That's more than likely why we're talking about nickel and cobalt-free products. But really, to set the stage, I think it's important to walk through just a few high-level items about the EU MDR and some of the updates. So the EU MDR, the European Union Medical Device Regulation, replaced the older Medical Device Directive, the MDD. The MDR was established really with the purpose of putting stricter regulations on product life cycles and increasing the overall product safety, ultimately with patients in mind, right? What is the safety factor for patients? What is the testing? And what are those life cycles? Under the old MDD, compliance was simply easier. It had CE markings and basic labeling. But the EU MDR imposes stricter requirements. Those requirements are just a list of few off the top of my head: labeling, clinical evaluation, chemical composition, which is what we're going to be talking a bit about today. So I think it's important really to kind of walk through what it means for OEMs and how Carpenter can be there to support. So again, for a little bit more background, regulation has upclassified cobalt. Cobalt is now classified as a carcinogen, a mutagen, and a reproductive toxin. So from a chemical standpoint, any device containing 0.1% or more cobalt must carry a warning label. So that impacts many of the alloys that we've used traditionally in implants, right? Stainless steels and cobalt-chrome alloys alike. Beyond that, up to 15% of the population is sensitive to nickel and cobalt, driving further patients' sensitivity concerns. And we're going to talk a bit about BioDur 108 and how that eliminates some of those risks by being both nickel-free and cobalt-free, while also boosting mechanical performance to drive further design. The last thing on the slide, beyond those comments, is that the EU MDR introduces unique device identification, stricter clinical evaluations, post-market surveillance, and, as I mentioned before, chemical substance control, including the cobalt restrictions. So that means many of the folks that are on the phone today, along with design engineers that may not be on the phone, we really need to think about the material choices as we move towards implants and instrumentation as this global community of component design changes. So we're going to talk a little bit about some of Carpenter's stainless alloys in this platform. So first of all, Carpenter has offerings beyond just simply the implantable products that I've talked about before. We have controlled cobalt content to really support and ease the burden of the MDR compliance across multiple instrumentation and implant materials. So many of these materials are alloys you've used today, you've used in the past, and many of these could be used as drop-in replacements with the added restricted cobalt content call out. And in case it's not very clear, or anyone is wondering, compliance is certainly not optional. It's essential if we are going to be playing as a global player in med device. So how do we get there, right? So we get there by understanding the melt technology and the history of the product. So at Carpenter, really, the melt technology is the foundation of the material that we produce, and ultimately the component performance that you see in your particular designs. So at Carpenter, we start with the raw material elemental additions, as I mentioned earlier on this presentation, and we really control every step of the melting process, which allows us to achieve super tight chemical control and also consistent microstructure. Cleaner melts lead to reduced inclusions, improve fatigue resistance, extend implant life. And it's really critical when it comes to patient safety and device reliability that we understand the history of our process, not only from a finished manufacturing, but also where the materials chemistry is born. Really kind of think of this as building a house, right? We start with the foundation. In this case, we're starting with quality at the melt and we're maintaining it. We don't just sort it in at the end of the process. So let's maybe one step further into cleanliness. So cleanliness in material it's absolutely paramount, right, to the device performance. I just mentioned a few things in the last slide, but again, the cleaner of the material through the options of vacuum melting or remelting helps minimize metallic inclusions, which can act as failure initiation sites. That enhanced cleanliness can improve fatigue performance, which is critical for implants that are subjected to cyclic loading, for example. Think of spinal rods, think of fixation screws. Microstructure, it helps deliver predictable microstructural properties, mechanical properties, and leads to better compliance and confidence in long-term implant performance. I mean, ultimately, fewer failures means better patient outcomes. So, we talked through some melt technology. So we're going to talk through even further some of the innovations where melting and chemistry control and metallurgy have really come together to address some of the EU MDR challenges. So as I pointed out before, right, so Carpenter has these refined scrap streams internally for us to drive input elemental additions and then melting protocols to produce low cobalt stainless steel variants. And the purpose of that, again, is to ease the burden of the MDR compliance. These materials, as I mentioned before, and also the implant materials that I'm showing on the screen, they're available today. So when Carpenter talks about engineered for MDR, like I have at the top of this slide, we mean implantable materials with cobalt controlled chemistry in mind. Now, typically when the industry thinks of implantable stainlesses, most of our minds go to the 316 LVM, right? Now Carpenter calls that 316 LS, BioDur 316 LS. And 316 LS is an alloy that now today is a de facto cobalt-free material, as it's required by the latest versions of the F138 and F139 specifications. But really, this wasn't always the case, right? So BioDur 734, BioDur 108 were alloy developments at Carpenter designed to tackle the metal alloy or metal ion concerns, while also driving strength improvements well before any of the changes to the ASTM specifications. So before we go any further, I just want to take a minute and I want to explain why we just walked through a recap of EU MDR and why we're talking about cobalt melting, cobalt restrictions instead of the new advancements for BioDur 108. First of all, it's to call out how regulation is changing innovation. And secondly, it's to address potential CCM replacement concerns. So first of all, in regards to innovation changes, I just want to take it aside and talk to the group for a moment about what I've heard recently in my travels and the industry changes that I've heard, right? So recently, it's been reported at MedTech in Germany, and then it was reiterated again at OMTech in Chicago, that 50% of medical device manufacturers are deprioritizing Europe, and that 50% of R&D and innovation in Europe is postponed or shifted out of Europe. So that means if innovation is to continue in med device, it's likely going to be continuing through other regulatory infrastructures, right? Such as the FDA, for example. I'm not saying that's what will happen, but that could be, right? So if this is the case, it would not be unexpected for contract manufacturers, non-European OEMs, and tiered suppliers to be working with different materials as non-European areas serve to be the quote-unquote de facto testing platform for innovation, right? So what I'm trying to get to here is that means here in the United States, here under the FDA, or in non-European locations where there are different regulatory control systems, there's an opportunity for global innovation and an opportunity to work with advanced solutions to solve these global problems. So the other comment I had was about CCM replacement and some of the concerns. So at Carpenter, we've developed alloys like BioDur 108, and we continue to iterate, right? This isn't something we just developed 15 years ago and it's stagnant, right? We want to be rooted in our technology and rooted in our innovation and rooted in collaboration with customers, but we need to be relevant and listen and get feedback and iterate and innovate. So we want to deliver the performance and the versatility for next generation implants. So I guess finally, after 29 slides, let's dive into some BioDur 108 and discuss why I believe it is a game changer. So quickly, before we get into the new information, I just wanted to quickly refresh some of the folks that may not be familiar with this alloy. Again, BioDur 108 is a nickel-free, cobalt-free, nitrogen-strengthened, austenitic stainless steel, and it's covered under the ASTM F2229 specification, as I have here on the screen. It offers exceptional strength, corrosion resistance, biocompatibility, precedence of acceptability as an implant material. You can think of it as 316L's big brother. It's stronger, it's cleaner, and it's engineered for the regulatory landscape of these restricted materials. We do that by stabilizing the microstructure with nitrogen and also manganese, and that drives a stable austenite without the need for nickel additions. And this is really where the innovation of this alloy meets the compliance requirements that have been set forth by the EU MDR. And now, as part of this conversation, we've pushed the capability of the product even further. So first, I'd like to just be the first person to introduce each of you to our most recent white paper on this topic. Some of you may have seen me handing this out at OMTech, but BioDur 108 as a proposed alternative to cobalt-chrome molybdenum for articulating implants. So historically, we've shown that BioDur 108 can obtain some higher yield strengths through cold working, beyond 200 KSI, well above 316L, for example, and also well above the cobalt-chrome molybdenum material. However, the concern is oftentimes, well, what's the wear resistance? How can it be used in articulating components? And our recent investigations and also subsequent patent that I'll show on the next screen not only meets but exceeds cobalt-chrome molybdenum in strength and in wear resistance. So that means this could be a viable alternative for articulating components, such as hips and knees, really where wear resistance is critical. And again, because it's nickel-free and cobalt-free, it helps meet the EU MDR compliance and expectations of future designs without compromising some of the performance concerns. So I alluded to a patent, and in addition to the white paper, in 2024, Carpenter was granted a patent where we outlined a new process for this product. Specifically, we showed the benefits of strain hardening coupled with surface hardening. So the patent is certainly open to review to customers, and it really showcases the material's capability to obtain high strength, high fatigue, and wear resistance. But again, it does that while retaining the capability to support even further surface modifications for extreme high hardness capability. So the diffusion process that we list here in the patent are not coatings, but instead are options to diffuse hardening elements into the surface to further wear characteristics beyond the simple strain hardening. But now that I've said that, I just want to kind of go backwards for a moment, right? So I talked about potential for meeting wear resistance through cold work, and then I talked about wear resistance enhancement beyond that with a surface layer technology. But let's return to the strain hardening only. Let's just talk about the material that can be strain hardened by a cold work, and be very clear that the wear resistance that is critical for implants through hips and knees is achievable with strain hardening only. So in the recent study that we outlined in the white paper, we compared BioDur 108 to cobalt-chrome molybdenum and 316L using the pin-on-disc wear testing governed under the ASTM F732 specification. You'll see on the right-hand side of the screen that we have an additional decrease in the wear rate. On the left-hand side of the screen, increasing the cold work in BioDur 108 results in improved mass loss. Again, where lower is better during the pin-on-disc testing. So this is dramatically beyond that of what you would expect in a 316 stainless. And again, just to reiterate, this is strain hardening or cold work only. But we aren't here to talk about BioDur 108 as a potential replacement for 316L. That possibility is rather obvious. Instead, we're here to discuss the options for BioDur 108 as a potential replacement for cobalt-chrome molybdenum. So as you'll see, if you have an opportunity to walk through the white paper, in the white paper, we talk about how we down select it to an appropriate level of cold work, and also further details are in the patent. And with that down selection, we can get a comparable wear resistance of a strain hardened BioDur 108 to both the cobalt chrome and well exceeding the 316L. As you see on these slides here, the actual results that we're sharing, BioDur 108 demonstrated comparable mass loss and surface roughness to the cobalt-chrome molybdenum, even under a rather aggressive 1 million cycles on a pin-on-disc test. So this means that it may be a viable alternative to cobalt-chrome. After we completed the pin on disc wear test, we looked at surface contamination of the wear debris and also the overall pin mass loss. And as you can see in the mass loss diagram, which is just a truncated version of what I showed you a moment ago, and also in the images here, there's really no statistical difference between the two from a pin loss after 500,000 cycles. So let's shift into some of the further options we explored within the white paper, the surface engineering for even further improved properties. And really the purpose of this section is to talk about compatibility. When we talk about surface engineering, BioDur 108 is compatible with advanced surface engineering techniques, right? It's not mandated to meet the performance. It's not the gateway to meeting the wear resistance of cobalt, chrome, molybdenum, right? We can do that with cold working direct. However, it does show the compatibility of the material in diffusion hardening, such as salt bath nitriding, carburizing, boriding, or a combination thereof. Or on the right-hand side, surface coatings, like diamond-like coating, the DLC, for very low friction and also an incredibly high hardness. So these processes are somewhat standard, somewhat commonplace in the medical industry. We see them being used. And it really just makes BioDur 108 another option that is practical, that is scalable, and has potential as an articulating device material replacement. So now we're going to jump into some of the details of the patent specific to the information we had identified through the surface hardening techniques, and really just wanted to give some of the examples of one of the processes in our patent. Specific to that, nitriding was performed, and it was really to show the effectiveness and compatibility of BioDur 108 to this type of process. So what we see on this slide is a cross-section of nitrided BioDur 108 material, really showcasing the nitride layer and the base material. And once again, for those of you who have not reviewed the patent or are not familiar with the process, nitriding is just a low temperature process that diffuses nitrogen into the surface, which can create a very hard case layer of like 30 plus microns. And that's dependent really on the exact process, the base material, and the processor themselves. In our test, we were able to identify a hardness of approximately 1,500 Vickers at peak, which roughly converts to just above 70 HRC. There's not a great scale because 1,500 is actually beyond that. But what this shows is that we have even further wear resistance and improved fatigue life without compromising the corrosion resistance or the bulk properties within the BioDur 108, as we explain and identify within the patent. And this is really beyond what I showed in the previous slides where we talk about wear resistance versus cobalt, chrome, molybdenum. This would be even further, and those tests for wear have not been performed. Again, so nitriding, a diffusion process that's enhancing the hardness of the material itself, and it allows for the properties of the metal, the base properties of the metal, to continue to perform without the fear of a coating coming off, for example. Beyond the imagery I just showed that was somewhat simple in the last slide, we also tested nitrogen content for the nitrogen-rich layer. And what we found is really what you may expect, right? We had elevated nitrogen levels up to 30 plus microns, driving deep penetration of this extreme wear-resistant skin. The nitrogen layer not only increases the wear resistance, but further supports the austenitic structure of the base alloy and really contributes and preserves the corrosion resistance of that austenitic base material. However, I think this slide does a bit better job of explaining the material and the potential of the nitriding process. So first, again, the surface nitriding of BioDur 108 is performed at lower temperatures, and this is purposeful, right? It preserves the cold worked microstructure and the underlying strength, the underlying toughness, the grain size, the grain flow. But in doing so, the process creates this thin, hard case skin that's typically 30 plus microns thick, as I mentioned, and has a peak hardness around 1500 Vickers, or again, 70 plus HRC. So this really drives the wear resistance capability much higher, beyond what I shared in the comparison to cobalt chrome, beyond what the material's bulk capability would be, while maintaining that corrosion resistant, ductile, and fatigue properties of the base material. So the patent that we provided, right, the approach that we took combines nitriding with controlled polishing and machining, really so that we could ensure the nitriding layer remains compressive and it doesn't introduce harmful tensile stresses, areas that are inconsistent in the surface that could potentially drive cracking. So, we've done extensive testing, including some of the ASTM F732 wear evaluations and fatigue assessments that show that cold worked BioDur 108 and nitriding maintains that mechanical integrity while delivering greater than 50% wear reduction compared to some of the alternatives. And again, I would encourage you to check this out in the patent. So in short, when it's applied properly, when it's applied correctly, nitriding enhances surface performance without undermining the base material's capability for toughness and performance. Now, when it comes to nitriding, we know that there's a lot of options out there. And again, the purpose of this portion of the presentation is to show the versatility in BioDur 108 and really point out that it's compatible with different commercial practices that are commonly available in the industry, and really provide kind of that capability of surface hardening as an option for further exploration. And just quickly to note to everyone here, there are some differences, right? And I apologize for the images here where we have some slightly different etchants that were used. So I apologize for some of the over etching here in the central image. In addition to nitriding, BioDur 108 is also compatible with surface coating technologies. So we did confirm in part of the patent that DLC, or the diamond-like coating, is compatible and they do not degrade the matrix. Now the thickness is a little bit thinner, right? But they can provide an extremely hard surface beyond what can even be measured on the Rockwell scale. Again, it can provide some low friction coefficient options, great for articulating components, and the biocompatibility of this particular coating has records and acceptable clinical use. So we have not tested in-depth, in situ, extensive testing on any of these coatings, nor does Carpenter offer these processes, but instead we're trying to show the compatibility of BioDur 108 with processes common to your industry today. So in summary, 2 more slides to kind of walk through just for food for thought. The BioDur 108 material, it's an FDA-approved material for implantable med devices today. It's got differing chemistry that helps ease the compliance with EU MDR. And all of the process steps that I listed in the past few slides, whether it's cold working, nitriding, DLC coatings, polishings, right? These are all standard in the medical industry, but they may not be needed for your particular application. As I said before, not all of them are necessary to obtain a material that exceeds cobalt-chrome molybdenum in strength, in fatigue, and in wear resistance. From a manufacturability standpoint, BioDur 108 is easier to machine than cobalt-chrome. So that can reduce the manufacturing complexity, the manufacturing time, manufacturing cost. And to boost that machining performance from the typical material that you may have explored in the past, we have some options for low temperature stress relieves that can be performed to even further improve machinability. So really the BioDur 108 material drives next generation designs by providing compliance to regulation, and really irrespective of the method of manufacture we chose in the patent or in the white paper, drives development for next generation components, whether they're for MIS, whether they're for patients, or whether it's driven in design performance. So all in all, BioDur 108 is an incredibly versatile material. Again, it's regulatory enabling, restricting that cobalt content, restricting the nickel content, and supporting those sensitivities in patients. It has customizable performance. It can be strain hardened to different property levels. And with its high nitrogen and manganese content, it obtains high strength while maintaining a fully austenitic structure. It has proven reliability. It matches or exceeds some of the legacy alloys that we've talked through in both mechanical and wear performance. And again, it has precedence of acceptability in implant applications. It has design freedom, right? It's compatible with surface engineering, with coatings, with varying methods of manufacture. And ultimately, it has this right here. It has Carpenter's collaborative innovation support, meaning we're here to showcase and support our materials. We're here to discuss and ultimately solve design roadblocks. We do that by showcasing our materials, talking with the industry, understanding what challenges and roadblocks exist, and working to break down those barriers. So again, Carpenter is not just a supplier, we're a technical partner. And I'll leave you with this. If you're facing a design challenge, a regulatory challenge, a manufacturing challenge, let's collaborate. Bring us your problems. And I think together, we can work together to understand what options are out there, whether we need to innovate, whether we have solutions today, whether we can leverage our knowledge across markets as we touch aero, consumer, magnetic, medical, work together to really shape the future of medical device design. So thank you.
Thank you, Ray, for that great presentation and sharing your insights and expertise. We really appreciate it. We have some questions from the attendees, so I'm going to dive right in if that's okay.
Absolutely. Sure.
What ultra-high molecular weight polyethylene was used for the POD testing? It's one of the questions.
I actually don't know off the top of my head. That might be in our patent, but if you'd follow up with me afterwards, you can get my contact information direct. I can put you in touch with the exact R&D engineer that performed the test. Again, I don't know the answer to that, but we'd happy to help and talk with you after the presentation.
Absolutely, thank you. Has wear testing been done on the nitrided surfaces compared to cobalt-chrome? Was another question.
Yes, so some of that information is listed in the patent. We also have internal information beyond what is in the patent. Again, that's another area where if you'd like specific collaborative information, reach out. Again, you can contact me direct. I'm rdufresne@cartech.com, and I can put you in touch with the R&D expert. We have done some of the testing. Some of that is internal information, but we'd be happy to work with you and provide some data.
Great. And a reminder, you can use the Q&A button at the bottom of the screen to submit your questions. But, you mentioned the nitrided surface layer on BioDur 108. You said it was about 30 microns. Is there a possibility of improving that depth layer? And it's a two-part question. For most applications, 30 plus micron depths of surface modification should be enough, but do you see any scenarios where a larger depth would be required?
Yeah, so I would say in the slides I showed 30, I showed 40, I showed actually up to 50, and I would say every application is different. So depending upon which company you're working with, we've seen up to 50, but we can work with you directly. We can get an understanding of your particular application. Sometimes there's design constraints, tight corners, things like that affect the capability of the material. And I would say, depending upon your exact design, right, we can work with you to get an understanding of what might be the preference for the product. I would, again, be happy to pull in our R&D expert that's been working specifically on this project. If you have a design need beyond, the 30, beyond the 40, beyond the 50, we just simply didn't push it any further than that. And 30 has been somewhat of a consistent kind of target that we've heard from feedback in the industry, but we'd be interested in talking with you further.
Another question is, you mentioned nickel-free. What does nickel-free mean specifically, and what is the max nickel content?
Sure. I'm not sure who asked this question, but very astute of you. You must be very familiar with the alloy. So if you look at the data sheet for the alloy, you'll see that the data sheet points to the, I believe, 0.1% max. But really, we can go quite a bit tighter than that. So if there is interest specifically on locking down nickel further, we would be open to supporting a 0.05 max for a nickel content. So you're right. We're never going to get to zero. So essentially, nickel-free is the term we use, and that really supports the nickel sensitivities at that 0.05% max.
Great. Someone asked, can this material be cast or available in powder for additive manufacturing?
I didn't catch the question. Could you repeat it?
Sure. Someone asked, can cast or available in powder for additive manufacturing?
So the material, it has been produced in the past for additive manufacturing through a powder. Through a casting operation, it may be challenged based off of the high levels of nitrogen content within the material. So there would be controls that would need to be put in place from a casting operation to maintain the expected nickel content. From a casting perspective, what I would actually encourage you to investigate instead would be similar to how the aerospace industry produces a warm forged product. So purchasing a slug of material that is a near net shape, going through a warm forging operation to impart strain hardening into the material, at the same time building your product based off of a wrought microstructure. So that is sometimes done in a precision forging process today for CCM, and is commonplace within the aerospace industry to forge near net shapes on finished components. Again, that can impart the strain hardening portion of the product, boosting the mechanical properties while also boosting the wear resistance and getting you in near net shape for that finish machining operation. Again, casting of the product, two things. And one, again, from a chemistry standpoint, the material has very high levels of nitrogen, which would need to be accounted for in that method of manufacture. But two, it would result in a product that does not have the strain hardening necessary to boost the mechanical properties.
Gotcha. It's that increasing cold work improves wear resistance. Is that something that is typical for other stainless steels, or is that unique to BioDur 108?
No, it's not unique to BioDur 108. The BioDur 108 material, I would say, has a better response. So, materials, typically you think of something like a 316 LBM, 316 LS, that material is going to get a boost in strength and hardness. So arguably, yes, it would have improved wear resistance. However, BioDur 108, based off of its high nitrogen content and manganese base, we're able to get a higher wear and a higher abrasive wear resistance based off of the interstitials of that nitrogen, right? So yes, other materials can provide a wear resistance that is improved, but it's going to be, nearly negligible. Whereas BioDur 108, you get a wear layer that's actually, quite substantial and throughout the cross section of the product. So not just a diffusion coating, not just a surface coating, right? This is a product that has a high wear resistance through its base microstructure. And again, born out of the chemical differences within the alloy plus the strain hardening operation.
Thank you. Last one, we're winding down with time here, but from the patent, it looks like the BioDur 108 is unique in combining high manganese and nitrogen. How do these elements help you achieve safe implants without nickel or cobalt? Are there trade-offs?
Yeah, so really, BioDur 108, again, with the nitrogen content that has been used, it achieves biocompatible performance, again, that has been approved within the industry. It has precedence of acceptability within the industry. The nickel content that has been removed, again, can challenge the austenitic microstructure. So manganese and nitrogen stabilize the austenitic microstructure, making that the material is non-magnetic, making the material cold workable, and giving the material a supported corrosion resistance beyond your standard, 18.8, 18.10, like a 316 stainless. So manganese, not only does it increase the capability for forming and locking in that austenitic microstructure, but it also gives things like hot workability as well. So when we talk about the manganese added into the material, again, in a product that has precedence of acceptability, that's going to drive some of these forging operations beyond what you would typically expect in your standard austenitic stainless steels. And really, the high manganese materials, high nitrogen materials to stabilize the austenitic structure have been used in this industry and others for years, right? We think about the 2213.5. We think about the BioDur 734, materials that have acceptable use with higher manganese contents. Really, the trade-off isn't there, right? We have a good performance with good toughness, good ductility, and high strength, stabilizing a microstructure that is applicable for these type of implant applications.
Great. Well, we'll leave it there, Ray. Thank you again for the great presentation and discussion. We always appreciate you sharing your perspective and expertise. I also want to thank the attendees. Hope you took something away from this discussion this morning and head home with some valuable information. Just to let you know, an on-demand version of this webinar will be published on bonezonepub.com, and you'll receive an email when it's available. So thanks again. And with that, I hope everyone has a great rest of the day.
Thank you all. Have a great day.